Right, lesson 81, page 500, 81 out of 86. I'm hoping to have them all done this week. I'm pretty certain I will. 6 to go. And then some revision for you. Page 500, 18.3, motion under gravity 2. So this is, oh, what on earth is that about? We don't want that, do we? There we are, motion under gravity 2. When an object moves vertically under gravity, we usually assume that it's a particle, i.e. it has no size and no spin, and that there's no wind or air resistance. Its acceleration is g meters per second squared downwards. However, an object thrown into the air is usually a projectile with displacement and velocity in 2 dimensions. This means that to investigate the motion of a projectile, we will often need to use trigonometry to resolve velocity into horizontal and vertical components. For example, consider a particle which is projected from point O, I'm going to draw it like on a graph here, on a horizontal plane with a speed of 25 meters per second at an angle of 30 degrees to the horizontal. So, does that look like 30 degrees? 30 degrees there, 25 meters per second. So this is going to go off like this. That's supposed to be symmetrical. Okay, right. So, resolving horizontally, we can get the initial velocity. And let's do this in a different colour here. It's here and here. So this is 25 cos 30 degrees, because this is adjacent to the 30, and 25 sine 30 degrees. So your initial velocity, or our initial velocity, is 25 cos 30 degrees in the I direction. I haven't talked about I and J in the book, but you can think of it like that as well if you want. Plus 25 sine 30 degrees in the J direction. J is 1 unit vertically, I is 1 unit horizontally. Okay, and then they've gone on to work out 25 cos 30 is 21.7, 25 sine 30 is 12.5. It's also useful to use this notation as well. Cos 30 degrees, 25 sine 30 degrees. Okay, anything else we need there? I don't think so. We'll also need to use the equations of motion for constant acceleration. Remember that g will always act as the vertical component of acceleration in a downwards motion. I.e. negative j, that means. Assuming there's no air or wind resistance, there'll be no horizontal acceleration, so horizontal velocity is always constant. Right, the equations of motion are, recap, we've got, I'll put them on the next slide because we can use them over here. V equals u plus at, s equals ut plus a half at squared. And these are vectors. T is the only one that's not a vector. S is also Vt minus a half At squared. V squared equals U squared plus 2AS. And S equals a half U plus V times T. Right, a particle is projected from point O on a horizontal plane with speed 40 meters per second at an angle of 30 degrees to the horizontal, and it lands on the plane at A. Taking g is 9.81 meters per second squared, work out how long it was in the air, so that's the time. The distance OA, that's S horizontally, and the greatest height reached. That is, well, the greatest height reach, that's when the vertical component of velocity vertical component of velocity equals 0. Okay, so that's the, the first one, it's the time when the vertical component of displacement equals 0. So I'll just do a little diagram just to illustrate all these bits here. Okay, so if we've got this particle flying through the air, no, it's more symmetrical than that. There we are. Okay, so it starts here. So if you like, these are the J's, or the vertical. These are the horizontal, or the I's. And what we've got is, so how long it's in the air. So it starts here, it's back it's back down there. Can you see that the vertical, at that point there, the vertical component of displacement equals 0. It's got a horizontal component, but not a vertical one. The distance is, so you find the time. So this one, this is OA. So that's S horizontally. Now this other one here, just at this maximum here, what you find is it's always got a horizontal component of velocity, but just at that top one, at that top point there, we've got the vertical component of velocity equals 0, because it just stops moving upwards and then starts coming back down again. So gravity wins at that point. Right, so we are given the initial velocity. It's 40 cos 30 degrees in the I direction plus 40 sine 30 degrees in the J direction. Okay, that's what I did in red on the other page actually, so I'll do them in red again. It goes like this. So that's the 40 degrees. This one here, this is opposite. So that one is, oh, it's not 40 degrees, it's 30 degrees. And it's 40. So that one is 40 sine 30 degrees because it's opposite. This one is 40 cos 30 degrees because it's adjacent. Acceleration is 0 in the I and it's minus 9.81. It says to take up there, look, in the J. So minus 9.8. Okay. And anything else? So part A, how long was it in the air? So for part A, when it lands, we've got S is unknown in the I, but it's definitely 0 in the J. Okay, so because we've got, now you see here, because we've got these 3 for the J components, we haven't got them for the I components, but that doesn't matter. We've got 3 in the J components, so we can work out time. So it's S equals UT plus a half AT squared, because S is what we want. No, S is, we know S is 0. T is what we want. U we know, and A we know. So we substitute it in. So 0. Sine 30 is a half. Get that on your calculator. So this is 20J. So it's 20. I don't need to write J. So we can just say this is going to be vertical. 20T, and then a half of A is minus 4.905 times T squared. So therefore, 0, factorise with the T, 20 minus 4.905 T. So therefore, T is 0, which is at this point here, and it has got a vertical component of displacement 0 there, or that should be there, an extra t there, because that should be t squared, the 4.905. Or 4.905t equals 20. So t is 20 divided by 4.905. Calculator, there it is. Just looking at the answer in the book, it's slightly different. 20 divided by 4.905 is 4.08. 4.08 seconds. G is given to 3 significant figures, so we need 3 significant figures for our answers. So I've done that one. Right, the distance OA okay, so now that we've got the time, this is going to be, and do this one in a different colour. So when it lands, we know T is 4.08, and we've just worked that out. So now we can use these to work out when it lands. Okay, this first one, I used the yellow. This all came from the yellow. There, that all came from the yellow ones. This next one, I'm going to do it with the green, because the distance O to A is horizontal, so we want the eyes. And if we look in the eyes, I've got U, I've got A. I know that U is 40 cos 30, A is 0, S is unknown, that's what we need to work out, and T is 4.08 seconds. So we can use our S equals UT plus a half AT squared to work out where it lands. S equals UT plus a half AT squared. This one is horizontal. Now S is equals to 40 cos 30 times, I've got this answer on my calculator, but it's actually 20 divided by 4.905 for accuracy. Now acceleration is 0, so that's good. So what I need to do now, 40 cos 30 on my calculator times 20 divided by 4.905, 141.3 metres. S equals 141 metres to 3 significant figures. So let's do some of this in green. All those figures are from the green. Okay, this one was to 3 figures as well. Okay, so that's part B done. And part C, the greatest height reached. I need to do this on a new piece of paper. So I've already said that at the vertical, at the max height, the velocity, the vertical velocity equals 0. So vertical means we're looking at the J's. So we're in here again. We've got an U, we've got an A. We know that V is 0. What's it say? The greatest height one, S. We've got U. So from the J components, because we're looking at vertical, we've got U is 20J. A is minus 9.81. I'm ignoring the I components here. I feel a bit naughty, but acceleration is, I've got acceleration. The max height, V, is 0, j. And we need to know the s. So we can do v squared equals u squared plus 2as. So therefore 0 squared is 20 squared plus 2 times minus 9.8 times s. So therefore s is going to be 400. So if we add all that over there, 20 squared is 400. And then we divide by 19.6, which is 2 times 9.8. 400 divided by 19.6 is 20.4 meters to 3 significant figures. Okay, so we just use, I've ignored the I components. Okay. Right, next one. Example 2. A particle is projected from a point O on horizontal ground with initial speed 12 meters per second at an angle of 60 degrees to the horizontal. Taking g is 9.8 meters per second squared. Work out its height above the ground after travelling 7.2 meters horizontally and its speed and direction at that instant. Right, so diagram here, it shoots off like this, that's 60 degrees, that's 12 meters per second. G is 9.8. Work out its height above the ground after travelling 7.2 meters horizontally, so we need to work out where it is. And its speed and direction at that instant. So u is 12 cos 60 degrees in the I direction, 12 sine 60 degrees in the j direction. Acceleration is 0 in I and then minus 9.8 j. S is 7.2 in the I and unknown in the j, that's a question mark. And then it's speed and direction at that instant. Right, we're going to work out the time first of all, using these here, because we've got 3 there, so we can use them to work out the 4th one, the time, and then we can use that time in there to work out that j. So there we go. So we've got S, U, A and T. S equals UT plus a half AT squared. And I'm going to use the horizontal ones to find the time. 7.2, 12 cos 60 times T plus a half AT squared plus 0 because of that A. So therefore T 7.2 divided by 12 cos 60 degrees. 7.2 divided by 12 divided by cos 60 degrees. 1.2. That's a nice round number. Ah yeah, cos 60 is a half. That's why it's come up as a nice rounded off number. So the time is 1.2 seconds. So if we substitute this in now vertically with our new answer, t is 1.2 seconds, we can get S equals UT plus a half AT squared and use vertical numbers this time with t is 1.2. So S is 12 times sine 60 degrees times 1.2 seconds. A half of A is minus 4.9, and T squared is 1.2 squared. So all that plugs into the calculator. 12 times sine 60 times 1.2 minus 4.9 times 1.2 squared, 5.4, and it's 2, isn't it? 5.4 metres to 2 significant figures. Okay. And its speed and direction at that instant. Okay, so to work out its speed and direction, I need its velocity. And the magnitude of the velocity is the speed, and then we can use the angle. Work out the angle using trigonometry. So B, I'm going to use V equals U plus AT, and I'm going to combine them together because I need both parts to work out the speed and the direction. So U is 12 cos 60 degrees, 12 sine 60 degrees, plus A, which is V equals U. A is 0 minus 9.8, and T is 1.2. Okay, so 12 cos 60 is 6, and then 12 sine, open bracket, 60 degrees, minus 9.8 times 1.2, I'm doing all this on the calculator, minus 1. Sine 60 is root 3 over 2, so it's 6. I'll just write in a rounded off answer. It's minus 1.3677. Okay, so the speed is going to be the square root of 6 squared plus minus 1.3677 squared. So I've actually got the unrounded off answer on the calculator, so I'll use that. So it's answer squared plus 6 squared, which is 36, and then square root of that answer. So it's 6.15. 6.2 meters per second, and the angle is going 6 across and minus 1.3677 down. Just remove that little bit of. So the angle, because of the minus, it's going below, so it's actually on the way back down. So it's doing something like this. It's gone up and it's come back down again. That's 7.2 because of the minus 1.3677. Tan inverse 1.3677 over 6. That's opposite over adjacent. Tan inverse, shift, tan inverse, open bracket, 1.3677 divided by 6, close bracket, is 12.8. 13 degrees below the horizontal. And that's to 2 significant figures. Okay, so that's that one done. Example 3. I like doing these actually. A girl throws a stone horizontally from the top of a 40 metres high cliff. .40 metres high. So this stone gets thrown horizontally, and it's just sufficient at a speed which is just sufficient to meet the water's edge 50 metres from the base of the cliff. So she throws it off like that. She's got perfect aim. Oops. Let's get that off there. And it lands 50 metres away. That's a bit messy there. I'm not quite happy with that line there. Just rip it out. So it's something like that, 40 metres. Acceleration, gravity, acceleration, so it's minus 9.8 metres per second, which is 9.8 metres per second squared downwards. Anything else we know? Nope. So U, it's 40I plus 0 in the J. We want the initial speed. It's not 40 there. 40 is the height. We don't know what that is. I'm going to say the initials. So it's just U. So U is something in the I. I'll call it UX. And it's 0 in the J because it's horizontal. Acceleration is 0 in the I, minus 9.8 in the J. And the initial speed, want to know the UA. We know that the displacement is 50 in the I, minus 40 in the J. So we can work out the time using this lot here for the stone to land in the sea, and then we can put that same time into those and we'll be able to work out the U. So that's our strategy. So we'll start with the vertical components to find the time, because we've got 3 there. And we've got U, A, S, and we want T. So it's going to be S equals UT plus a half AT squared. So minus 40 is 0 times time. Half A is minus 4.9 times T squared. So T squared is actually 40 divided by 4.9, because that goes and the 2 minuses can cancel out as well. So therefore T is the square root of 40 over 4.9. I'll just leave it like that for now to keep it accurate. And that's all come from the yellow, that time, vertical. So that time that we've just got, I'm going to put into there. T is, I'll just, don't need to do anything else there. So I've got U, A, S, and we want time. This is going to be horizontal. Horizontal with time, square root of 40 over 4.9. So it's that lot there plus that. So it's going to be S equals UT plus a half AT squared. So this 50 is our unknown U times the square root of 40 over 4.9. And then our half AT squared is 0 because of A 0. So therefore U is 50 divided by the square root of 40 over 4.9. So let me do the square root of 40 divided by 4.9. First of all, this calculator is a bit weird. Doesn't actually, it's a bit old-fashioned. Not one that I normally bring to school, to university. 40 divided by 4.9, that's 2.857 seconds. 50 divided by the answer, 17.5. Check my answer in the book. Yep. So U is 17.5 metres per second. Okay, and that's all come from green considerations. Okay, and the speed and direction of the stone when it hits the water. So this is another piece paper. So for the speed and direction, I need the vertical. No, I don't. I need the velocity. Because the speed is the magnitude of the velocity. In the direction, we can do inverse trig on the I component and the j component to figure that out. Right, so it's going to be v equals u plus at. I need a new piece of paper. And I need the vertical and the horizontal. So v, our u is 17.5i plus 0j. Our a is 0 minus 9.8. And our t is the square root 40 over 4.9. Okay, so put all this together. Sorry, that's u, that one. So v is u plus a times square root of 40 over 4.9. So the velocity, 17.5 on the top because of that 0 in the second vector there. And then the next one is 0, and then it's minus 9.8 times the square root of, open bracket, 40 divided by 4.9, close bracket, minus 28. Just checking my answers there. Yep. So the speed is the square root of 17.5 squared plus minus 28 squared. Square root of, open bracket, 17.5 squared plus minus 28 squared is the same as plus 28 squared because the minuses cancel out. So I've just typed that into my calculator. And that works out as 33.0 meters per second. Well, and it probably wants its two significant figures, so it's probably 33. Then the direction. So this is going 17.5 across and 28 down, going in this sort of direction here. Like so. I've exaggerated that a little bit. 17.5 minus 28. So we do tan inverse 28 over 17.5. .58 degrees. Same as in the book. 58.0 degrees below the horizontal. Okay. And then I think this is the last example. A projectile is fired at 50 meters per second from ground level and strikes a target 100 meters away and 20 meters above its point of projection. Just trying to imagine what's going on here from ground level. Sounds like somebody's laid on the ground with a gun and it's fired upwards. Yeah, I've got it. So it's fired, there's 100 meters away and 20 meters up. Okay, so I won't write meters everywhere. So you can either hit this, you're from ground level, so it can either go up and then down again, or it can go straight across and catch it on the way up. That's not very good. It can either catch it on the way down or catch this target on the way up. Okay. So there's two possible angles. There's a steep one and a not so steep one. Okay. So we've got theta, call it angle theta and angle phi. I'll just have to zoom in a bit to get that working, make that look. Get it a bit neater. If I zoom in, it looks a bit neater. Right, so that can be the angle theta. That one there can be the angle phi. There we go. So the speed is definitely 50 metres per second for both. But we've got theta and phi. Okay. So U, let's do theta first of all. U is 50 cos theta in the I direction, 50 sine theta in the J direction. Acceleration is always 0 in the I direction and minus 9.8 in the J. In fact, this is going to work for both. I might change this in a minute from theta to just a general. No, I'll come back to that in a minute. T we don't know. We know position. It lands at 100 in the I, or hits the target, 100 in the I, plus 20 in the J. Anything else we know? Actually, if I call this, I've got a better idea. Call this theta 1 and theta 2. Whoops. Theta 1, theta 2. I'll do the general theta here and then we'll pick out the theta 1 and theta 2 at the end. Okay, so what do we need? Two possibles. So we want the thetas. Right, so we can work out tricky, this one. Let's work out, it's either V or T. We don't know anything about V, it has to be time. So we've got to work out the time for each. Just have a little think here. It's definitely going to be S equals UT plus a half AT squared for both of them. I'll do it in this way because it gets a bit neater this way. So that's the S. A is 0 minus 9.8. And U is 50 cos theta that way, 50 sine theta vertically. So 100 over 20. I'm going to use S equals UT plus a half AT squared. S 120 is U, 50 cos theta, 50 sine theta, U T plus a half A T squared. Okay. Yeah. So if we look at the horizontal components first of all, and the reason why I'm doing that is because that 100 and that there and that 0 means I can work out that cos theta over that t as well. Cos theta is 100 divided by 50t. Okay, so look, horizontal 100 is 50 cos theta times t. So therefore t is 100 divided by 50 cos theta, and they cancel to make it 2. So t is 2 over cos theta. And then look at the vertical components. Vertical components. 20 is 50 sine theta t. A half of 9.8 is minus 4.9. t squared. Now t is 2 over cos theta. So I'm going to replace, this needs a new colour, I'm going to replace this t, 2 over cos theta, into there and there. Okay, so we have 20 equals 50 sine theta times 2 over cos theta minus 4.9 times 2 over cos theta all squared. Definitely need a new piece of paper for this one. And just do a bit of simplifying here. 20, right, 50 times 2, here look, 50 times 2 is 100. And then look, I've got sine theta over cos theta, which is tan theta. 100 tan theta. And then I've got 4.9 times 4 with a minus sign. So 4.9 times 4, 4.9 times 4, 19.6. And then over cos squared theta. And this is where I'm going to get my new piece of paper. I'm going to write that up on the next side. 20 equals 100 tan theta minus 19.6 over cos squared theta. Now if you remember, 1 over cos squared theta, look, the first letter is a C, so that's sec squared theta. So I've got 20 equals 100 tan theta minus 19.6 sec squared theta. Then, if you remember, we've got sine squared theta plus cos squared theta is always 1. And we want sec squared theta. So if we divide this by cos squared theta, we get the sec squared theta. So we divide everything else by cos squared theta. So we do the same thing to each side of the equation. We get sine squared over cos squared, which is tan squared theta, plus cos squared over cos squared is 1, and that's sec squared theta. So that goes into there. So we have 20, I'll put this down, I need all this room, I'll put it down here. 20 is 100 tan theta minus 19.6 tan squared theta plus 1. I'm going to expand those brackets now. 20, 100 tan theta minus 19.6 tan squared theta minus 19.6. That's multiplying everything inside that bracket by 19.6, 1 minus 19.6. I'm going to collect everything to the right here. 19.6 tan squared theta minus 100 tan theta plus 39.6 is 0. Quick check. The book's used G as 9.81. I've used it as G as 9.8. So their answers are slightly more, got a few more decimal places than mine, but apart from that, we're fine. Right, now this is, if we let tan theta be x, we've got 19.6 x squared minus 100x plus 39.6 is 0. So we've got a quadratic, and we can solve this. X is minus the b, which is minus 100, plus minus the square root of the b squared. That's the a, that's the b, including the sign, and that's the c. B squared minus 4ac, if you remember, 4 4ac all divided by 2a. 2 times 19.6. If you've forgotten where that comes from, if you've got ax squared plus bx plus c is 0, x is minus b plus minus the square root, b squared minus 4ac all divided by 2a. Okay, so x is 100 plus minus the square root of, I'll just do that on my calculator, 100 squared minus 4 times 19.6 times 39.6, 6,895.36 over 39.2. Okay, so I'll just do a square root answer. So x is 100 plus minus, I've got the square root of that now as 6.26099, etc., etc., over 39.2. 100 plus answer divided by 39.2, which is, oh no, I did that wrong, 100 plus 6, my calculator's not as advanced as I'm used to at work, 100 plus 6.26099 divided by 39.2. No, I'm getting different answers from the book. I've got the same numbers. (39.6) minus 100, yeah. Minus b plus minus square root b squared minus 4ac all over 2a. I'm certain it's this calculator that's not really very good. The buttons don't work, so it seems to be under the light, so I can watch what I'm doing a bit better. 100. Just check I've got everything right. Nearly there. 100 squared minus 4 times 19.6 times 39.6. 68, yep. Square root answer. 80. Oh, that was miles out there. Don't know where that came from. 83.0383, etc., etc. So x is 100 plus 83.0383 divided by 39.2. X is 4.67, I've got. 669, or 100 minus 83.0383 divided by 39.2, 0.433 to three significant figures. So that means, so x is really tan theta. So tan theta 4.669. Theta is tan inverse 4.669. Shift tan inverse 4.669. 77.9, so we'll call that 78 degrees. Also, it's also equals to 0.433. So theta is also equals to tan inverse 0.433. Shift tan inverse 0.433. 23.4, 23 degrees to two significant figures, because I've used 9.8. So an answer there, that would have been my theta 2, and that would have been my theta 1. Because if you remember, I had my theta 2 as the higher one. There, look. So that was theta 2 and theta 1. Okay, so there's two answers, and it's come up because of the t. It's come up because of the t squared there, and because t is in terms of an angle theta. So you're ending up with a quadratic with angles in, and you end up with two answers.